So here's the wall. Here's the book. There's our free body diagram. Let's put the wall in there just to give us a bit of a reference. Um, well, Cairo, what are the forces acting on the book? Get the obvious one. Which way? I agree. Was the book accelerating downwards? Was the book accelerating upwards? So there has to be a force the same size as mg pointing up. What force is that? I'm not sure yet. I'm going to leave it blank, but I'll come back to it. What other forces were acting on the book? Well, there was me pushing with the meter stick. Let's call that in that direction F applied. Was the book sinking into the wall like quicksand? Was it flying off of the wall like Superman? So what else do I need? Yeah, a wall can exert a normal force as well. You can think of the wall as the ground just tilted 90 degrees. The ground will apply a vertical normal force. A wall will apply a horizontal normal force. Cairo, does that give you an idea of what you, not F applied, Mr. Dewick, FM, what you think that vertical force might be? And friction equals what times what? Mu times the what? The harder I push, the bigger the normal force, the bigger friction is. Now, you may be saying, okay, whatever. Well, I like to show you the physics of common, everyday, ordinary stuff. I'm sure all of you, at least once, have carried something heavy like this. Sorry for those of you on YouTube, you can't see what I'm doing. But my fingers are purely pushing horizontally. What am I doing? I've got a normal force this way, a normal force this way. I've got a force of friction from my index finger. I got a force of friction from my thumb. And when I add those two together, they equal mg. What's going to happen if I relax my fingers? It's going to, first of all, you'll see it start. Yeah, you could see right at the equilibrium point where it just started to move. I had just made friction too small to cancel out gravity. Maybe you're like, whatever. I kind of like that. I've carried stuff like this all the time. It's a neat free body diagram. I like explaining the physics, then, of stuff you do all the time. It's the thing with me. All right. That's not today's lesson. Ben, what's the title of today's lesson? Lesson 7. What happens if there's more than one mass attached by strings? So it says, in these problems, we have several objects connected by strings. We're going to look at two masses all the time. We'll do a couple with 3 masses so that you know how you could extend it to 4 or 5 or 6. We're not going to bother going into 4 or 5 or 6 masses. And in fact, I'll even tell you on your test, I won't give you a 3-mass question. I'll do a couple in the homework just so that you know it works. We can extend it to as many as we need. We're going to add a restriction though. Again, sorry to those of you on YouTube. We're going to say if you have 2 masses connected by a string, like this, what you're not allowed to do is jerk on the rope. This is actually called a jerk in physics. And the physics of a jerk, it's actually pretty difficult. It's a 4th derivative for those of you that are in calculus. What we're going to say, if you're pulling, the poles have to be smooth. Now, what does that mean? That means if the mass in my left hand moving to your right is accelerating at 2 meters per second squared, this one is accelerating up at 2 meters per second squared. Different directions, but same magnitude. So what we can do then, Jaden, is we can treat this as one big Ubermass. Jaden, you and I are going to do this example 1 together. In fact, it's so easy, I'll bet you and I can do this in our heads. Are you ready? Here we go. Jaden, example 1 says, find, what does A want me to find? What does B want me to find? What we're going to do to find the acceleration of everything, we're going to write an equation for everything. To find an individual force, we're going to write an equation for an individual mass. I tried to emphasize the words everything and individual. Any suggestions on how we might start out? What might this be a good job for? Yeah. Now, you don't have to do it this way, Jaden, just so all of our work looks the same. If you give me more than one mass, I'm always going to move from left to right. You don't have to, but I'm always going to start on the left side of the picture and work my way across. And since they gave me a picture, I'm going to label the picture. You ready? Here we go. This 3 kilogram mass, what are the forces acting on it? Get the obvious one. Is there more than one mass in this question? Say yes. I'm going to call it M1G. Want to guess what I'm going to call the other mass? Yeah. Okay, is M1 sinking into the ground like, is it flying like, what else am I missing? What do we call that force from the ground pointing straight up? Bigger, smaller, or same size as mg? Is there more than one mass in this question, Jaden? Say yes. I'm going to call it normal force number 1 to go with mass number 1. I'll be lazy but organized. What else? Is this 20 newtons? Is this 20 newtons touching the 3 kilogram mass? No. What's touching the 3 kilogram mass? This rope. Do you remember, what do we call the force from the rope? You're feeling it right now. Starts letter T. Yeah. I'm going to go like this. Okay, I'm going to go like this. Tension. That's the free body diagram for the first mass. Now let's go to the second one. What are the forces acting on it? Get the obvious one. Which way? Is there more than one mass? I'll call it M2G. And then I think normal force number 2, yes? We have this 20. What do we call the mystery force coming from off of the page? Yep. Yeah, let's call it F applied. I'll put an arrow and I'll just write F app equals 20. I'll be organized but lazy. We're missing one more force. No friction. It says this is frictionless. If this had friction, I would say I like this question, I like this question. We'll get to friction on Monday. Friction just makes the questions, Jaden, I don't even want to say harder. It makes them longer, more writing, but it doesn't make them much harder. We're missing one force, though. Did anybody see it? This is a Newton's third law. Forces come in. Okay? Right here. Tension is what's tugging on the 3 kilogram mass. The 3 kilogram mass would feel tension tugging it to the right. The 2 kilogram mass would feel tension slowing it down. Okay, there's my free body diagram. What we're now going to do, Jaden, is we're going to write an equation for everything. What we're going to do is we're going to walk along the rope in that direction. Okay? We're going to start in the direction or on the side that we're accelerating to. Which way do you think this is accelerating? To the? So which is the winning direction? Same answer. So anything pointing to the right, I'll make positive, winner plus. Anything pointing to the left, I'll make negative, loser minus. You ready? Here we go. Who's winning? Start right here. And the first force I run into is F applied. F applied, winner or loser? Let's write down here, winner. And then I walk along the rope. The next one along the rope that I run into is this tension here. This tension here, winner or loser? It's pointing to the left, so minus tension. And then I run into this tension here. Yep. Have we reached the end of the rope? Yes. Don't put M1G or normal force. They're not along the rope. They're not going to show up in this equation at this point. So equals. Here's the only tweak we need to make to our winner minus loser. Jaden, do you notice we have forces from more than one mass on the left? I have to have more than one mass on the right. It's M all A, not just MA. What do I mean by M all, Liam? You're going to add them together. Put your pencil down, Jaden. Stretch. Serious. Relax. Oh. Jaden, why are you stretching? Why do I find these questions so relaxing? Every time you do them, you lose some tension. Oh, this is good. That's not my worst joke. It's going to get worse. Okay. What are we trying to find in part A? Oh, get the A by itself. Sophia's theorem. Not divide by M, but divide by M. Oh, let's do that on this line right now. Boom. Boom. Okay. So A equals, Jaden, what was F applied? Yep. And the M all, that's just going to be 3 plus 2, the mass of all of them. You might even be able to do this in your head, Jaden. What's 3 plus 2? 20 divided by 5 is? See, that's what I feel when I do math. You get a little nerdy adrenaline rush? Mommy, look what I did. Hey, Jaden, let's show off. Let's even go to 3 sig figs, 4.00. Units, Jaden, meters per second squared. Okay? Yep. You get extra points if you laugh? Sadly, no. I'll be impressed, though, if you can keep from grimacing, because it's about to come. Are you ready? Here it is. We're online. First of all, so to find the acceleration of everything, I write an equation for everything. Why can't I use, what does B want me to find, Ella? Why can't I use this equation to find tension? Yeah, we have a deficit of tensions. Yeah, this is a disorderly equation. One could say that since we have a deficit of tensions, you might say we have a tension deficit disorder. Yeah! It's a deficit of tensions. So we have a tension deficit disorder in this equation. Oh, Liam, come on. That's not just scraping the bottom of the barrel. That's lifting the barrel and seeing what's underneath. Oh. Okay. So Ella, that's the worst joke you're going to hear from me all year. To find an individual force, we'll write an equation for an individual mass. So it says to find the tension, we have to isolate a single mass. Let's look at the 3 kilogram mass right here. Very quickly, let's redo the free body diagram. It was M1G, normal force 1, tension. We're going to write an equation just for it. Which way is it accelerating, Ella? To the right or forwards? So who's winning? Who's losing? It's a trick question. So you have winner, no loser, equals, not M all A. Now we're looking at one mass. Which mass? M1A. Oh, Ella, do I know M1? What? And did I just find A? What? Like Jaden, can you also do this one in your head? 12 newtons. 12 newtons. Yeah. Siobhan, you know what would be really cool? It would be really cool if it didn't matter which mass we picked. It would be neat if we used the second mass, we also would get 12 newtons. That would be really, really cool. Let's try that. So the 2 kilogram mass, I believe, let's quickly sketch the free body diagram. It was M2G, normal force 2, F applied, tension. Let's write an equation for that mass, and we'll solve it for tension. And if we're lucky, maybe we'll get the same answer. Who's winning? F applied. Who's losing? There is someone pointing left. Yes. And we're going to stop there because we're just writing an equation for this mass. So it's going to equal not M all A, M2A, because we're just writing an equation for mass 2. Let's get the T by itself. What's right in front of the T that I don't like? Swappy dance time. Plus it there, minus it there. And so the F applied drops down like a domino. And instead of a minus T, it's going to be a minus M2A. And then do you mind, Siobhan? I'm going to put the T over there. What's F applied as a number? Minus. What's M2? What's A? It would be really cool if that also worked out to 12. Does it? Oh, that's so nice. So you can either do the questions twice to check your answers, or my rule of thumb is I do whichever is the least amount of writing. I would have used the first mass because you get the T by itself easier, but you'll get the same answer no matter what. That's our strategy. You give me more than one mass, I'm going to say that write an equation for everything to find the acceleration of everything, and it's going to be the same acceleration because they're connected by a string. Oh, you want me to find an individual force? I'll write an equation for an individual mass. We can even have something like this where you have a hanging mass with no external force. So I think the wheels are meant to indicate, Carson, that we can kind of ignore friction. Which way is this whole thing going to accelerate? I think right and down. You okay with that? All righty. Carson, what does A want me to find? And B says, you know what this is a good job for? Free body diagram. Let's do, and again, you could start with a 2.5. It's not wrong. Just so that all of our diagrams look the same, I just always start on the left and work my way across. So let's do the 6 kilogram mass first. What are the forces acting on it? Yeah, one. I'll call that M1G because there's more than one mass. And normal force number 1 to go with mass number 1. Is there a rope or string? So we have tension. Is there friction? I think the wheels are meant to indicate frictionless. But by the way, Monday will include friction, and all it is, don't write this down, is just one more loser, one more force in your equation pointing that way. It's not that much more work. That's the free body diagram for those. What about for this? Well, let's go systematically. The obvious one. M2G. Is it sitting on a surface? So is there any normal force? No. People get normal force loopy and start sticking it everywhere. Not if it's dangling, but there is a rope. Yeah, tension is pulling up on this one. Okay. Which way is this accelerating? You already answered this. You said the acceleration is in that direction. Yes? So I think what we'll say is anything, once it gets here, Ben, pointing down is going to be winner plus. Anything, once it gets here, that's pointing up, it's going to be loser minus. Is that all right? Let's start on, and again, it's going to be the same dealio. We're going to write an equation along the rope. This time, the rope has a 90-degree turn. That's all a pulley does, is it changes the direction of a force. It doesn't add or subtract force to it. So, who's winning? 2.5 is a mass, and that's not even anything from my free body diagram. From my free body diagram, what's causing this whole thing to start to accelerate in the first place? Winner. And then this tension here, loser. Walk along the rope, walk along the rope, walk along the rope. Is M1G in the same direction as the rope? Don't put it in. It's not along the rope. Oh, but tension, this tension here, if you follow it, follow it, follow it, when it gets to here, pointing down, and you've decided to let down be the winner, so winner plus. We've reached the end of the rope, equal sign. Do we have forces from more than one mass? We better have M all A. Carson, how's your day going? Put your pencil down. Stretch with me, baby. Come on. Come on. Oh, why are we stretching? Oh, I love it. These are like little spa treatments. Mr. Dewick, are you going to do that dumb joke every time? Maybe. What's A asking me to find? How would I get the A by itself? Yeah, let's do that on the next line. Now, if you want to show your work, you could already here go boom, boom, and then we can actually even go to numbers already. We can say, okay, A equals, what's M2? That's the word, this is messy. Let's make it a little neater. 2.5 G, 9.8, all over 6 plus 2.5. You want to practice typing these in. If you don't have the fancy schmancy fraction button, I think you're going to need to use brackets around the top and brackets around the bottom because there is more than one thing on the bottom. So 2.5 times 9.8 divided by 6 plus 2.5. There is a bit of a built-in error check here. You can survive without this, but Carson, suppose I cut the rope, cut this string right here, and now this is in free fall. What's the biggest the acceleration could possibly be in free fall? Is it being slowed down? You have to get an answer less than 9.8 in this situation. In other words, if you're telling me the answer is 17.9, you forgot brackets or you did something wonky. So there's a bit of a built-in error check. I have no idea. 2.88235, that there? To 3 sig figs, we'll store this on our calculator, but to 3 sig figs, 2.88 meters per second squared. Okay. Sophia, we're not done yet. There's a part B. Sophia, what does part B want me to find? It doesn't matter which mass, just this one last time, let's do it for both. And then from now on, I'll say to you, pick whatever's laziest. So if I was going to use the left hand, the 6, which way is the 6 accelerating? To the right. Which way is the winning direction? To the right. Who's winning? Who's losing? Yeah, if I was using that mass, it's going to be tension, no loser, equals M1A, because we're just looking at that mass. Or you could write an equation for the 2.5. Who's winning for the 2.5? Minus tension equals M2A. Which of those is less writing? I would use the first method, but let's do both. So let's say this half of the class, you're going to get the t by itself in the left-hand equation. You'll do the right-hand equation. It already is kind of by itself. So you guys can go straight to the answer. Those of us here, we need to do a swappy dance, I think. Yes, Sophia, because of the negative. It's going to be M2G minus M2A. That equals tension. It's going to be 2.5 times 9.8 minus 2.5 times, I'm going to use my answer button. You folks can just go 6 times answer button. We should all get identical, if we're using our answer buttons, we should all get identical answers. So I'm on this side of the room, so I'll do the 2.5 times 9.8 minus 2.5 times answer button. You folks are just going to go 6 times answer button. Did everybody get 17.294,117 if you use your answer button? And again, say the point being, doesn't matter which one you use. Pick whichever is the easiest. Sometimes one will be so complicated, even though it's less work, you might use the one that has more forces on it because you know them all. And it's like your comfort place. So pick whatever makes your life the easiest. But no matter what, for both of these, tension is 17.3 newtons. We're going to pause here. But on Monday, we'll include some friction. We'll include 3 masses. And then I'll give you a bunch of these to practice. But I'm also kind of hoping you're saying, you know what, aside from the M all A, nothing new today. I hope this was all familiar territory, because that's kind of the goal I'm trying to reach the point for. So you have some homework you can work on the take-home quiz. If you hustle, you'll have no homework for the weekend. Let me just pause the video.